Yeah, but I'm seeing this is old live. Huh? Okay. Yeah. Now I think I've taken the 1 minute.
Yeah,
Oh, I'm sorry.
I think the screen is not shared. All right, so can we get started? It's already live. Okay, welcome everyone to this second live session for the course on basics of materials engineering.
Ravi, am I live now? Can I start? Yes. Okay. Give me a minute. Yeah.
Can we get started? It's already live.
Okay. Welcome to this third live session on the basics of materials engineering. My apologies for the delay and also rescheduling from 4:30 to 5 because I had to go for another meeting which I could not skip. Anyway, so in the live session, this session, we will try to answer some of the questions that you guys have asked. The one question that many of you have asked was to show the solution of the question 4 of assignment 8. So that is something that I would like to do now. In the meantime, if you have any other questions, you can type in, and my TA will remind me if I have not answered any of the questions because he's also around. So the question that we have in the question 4 of assignment 8 is: you have a stepper shaft and which is actually, so this is our stepper shaft, and you have a point A, and you have a load B and loads point C and point D, and this is point E. Okay, so at point B you have 8 kilonewtons load, and at C you have 6 kilonewtons load, and it is known that the stepper shaft is supported using simply supported end conditions at point A and D. So let me draw the support conditions in a different color and the load in a different color. Okay, and the distances are basically this is 200 mm. From here to here it is 200 mm, and then the next point from here to here is about 200 mm, and here to here is over 100 mm, right? And here to here is 200 mm. This figure may not be to scale, please bear with me. And this is basically a circular shaft, and whose diameter, this diameter is 40 mm and this diameter is 48 mm, right? That's what is given. And this stepper circular shaft is rotating at a constant angular velocity. So it is rotating at, so there is no velocity fluctuation. It is rotating at a constant angular velocity and is acted upon by these two loads, 8 kilonewtons and 6 kilonewtons at points B and C. And the rod is made from rolled steel. So it's basically we are telling the what kind of a material whose ultimate tensile strength SUT was given as 600 MPa, and SE, that is endurance strength of 250 MPa. Okay, and the fatigue stress concentration factor in bending is given as 1.4, and the fatigue stress concentration factor in shearing is 1.2. So these two stress concentration factors are given for this region because you have a stepper shaft, because you have a change in geometry, then you expect to have some stress concentration there. And instead of you going about estimating these values, they are already given for you. Normally, in regular design problems, you will not be given these values, and you actually need to refer to the tables and then find these values if you want to solve the problem. But in this problem, it is given. Okay. And what is the factor of safety against loading for this system using, say, Goodman criteria? I think we have said that. What is the factor of safety against loading using Goodman criterion is something that we need to address. Okay. All right. So let us carefully think about how do we want to solve this problem. Okay. So here, if you carefully look at, in order to verify whether this problem is a time varying problem or not, or a fatigue problem or not in the first place, is something that we need to check. So since the shaft is rotating at constant angular velocity, that means if this shaft is subjected to some loads, suppose this guy is, suppose if the shaft is like this and then the shaft is bent like that, okay, using some bending moment, let us assume, then this part is subjected to compression and this point is subjected to tension if it is not rotating. But if it is rotating, this fiber in half a rotation will actually go to this place, and hence this material point would have experienced a compressive force. In that sense, it is a time varying load. At any point in the domain, the stress state is changing as a function of time because of the fact that the shaft itself is rotating, and hence it's a fatigue design problem. That is the reason why this constant angular velocity is an important thing to keep in mind. All right. Then we need to find out how do you go about doing the design. While you are designing a shaft, you should ensure that the maximum stress induced in the shaft is well within the allowable stress, whatever that allowable stress may be. So you need to identify what is the maximum stress induced in this shaft. So for instance, now you can idealize this as a simply supported beam subjected to 2 point loads at a distance of 200 mm from either ends, and then you need to check whether you will be able to calculate the maximum stress induced in the shaft and what kind of stresses are induced. Is it only a normal stress or you also have a shear stress? Okay, that is something that we need to take into account. All right. So now let us go about solving this guy. Let us idealize this as a beam, as a simply supported beam. Okay, and with the end supports here, point A, and this is point B, and you have, this is your point E, and okay, so let me, and this is point B and D. Please bear with me that it is not up to the scale, so you have to bear with me with that particular aspect. Okay, so maybe I will, so let me say this is E and that is B, and and that is C. Okay, so from here to here it is 100, and that is 200, another 200, and another 200. All these are in mm. Okay, and you have a load 8 kilonewtons and 6 kilonewtons. Now, most of you would have done your strength of materials class. So in the strength of materials class, you would have studied how do you calculate moment at each and every point. So let's draw the bending moment, shear force and bending moment diagrams. So let us first draw the shear force and bending moment diagram for this guy. So before drawing shear force and bending moment diagrams, we should know what is the reaction force at A and reaction force at B. So we know that when we want to do that, so what you need to do is you need to take equilibrium. So there are no forces in x direction. So let us say this is my x direction and that is my y direction. So I can say that RA plus RD for equilibrium, force equilibrium, should be equal to 8 plus 6, that is 14 kilonewtons. Right? That is your first equation. And the second equation, so we have done the force equilibrium. Now let us do the moment equilibrium. Moment equilibrium, because the fact that this is simply supported, the moment at the end should be 0. Right? So I am saying MA should be equal to 0. MA means moment about point A because of all the forces that are acting on the system. So that implies I come from this side, that is RD times 0.6 meters. I am writing everything in SI units, 0.6 meters, and then minus 6 into 0.4. Why did I put minus? Because this moment will create moment in this direction about A, and this guy will create a moment in this direction. So they're opposite sign. So that's why minus 6 into 0.4 and minus 8 into 0.2. Thus, that will be your moment at A, because the moment due to the reaction force at A will be 0 because the moment arm is 0. So this must be equal to 0. So that implies RD is equal to 6 fours are 2.4 plus 1.6 by 0.6. That is basically 4 by 0.6. That will be 6.67 kilonewtons. Right? Then using this equation, you found RD. Therefore, RA will be equal to 14 minus 6.67 kilonewtons. That is basically 7.33 kilonewtons. Correct? So this is your RA and RD. So RA you know now, that is 7.33 and this is 6.67. Okay? And now let us draw the shear force and bending moment diagram. So let me draw. Okay, so let me draw a base that is 0. Okay, so at support D, the bending moment will be 0 because it's free. That's simply supported. And then at point C, what will be the bending moment? At point C, that is moment at point C will be equal to RD into 0.2 because the distance is 0.2. That is equal to 6.67 into 0.2. That will be 1.334 kilonewton meter. So at here, let us say this is 1.33. This distance is 1.33. And similarly, at B, what would that be? MC will be equal to RD, that is 6.67 into 0.4 minus 6 into 0.2, because at C you have moment due to this load and also as well as this load. Correct? So that would be equal to 1.468 kilonewton meter. 1.468, that height. Okay, and then MA will be 0 anyway. But there is another interesting point here, that is E. Where do you think your bending moment is going to be? What will be the bending moment at E? So bending moment at E will be, you can actually add them, all of them, or you can come from this set, that 7.33 into 0.1. That is 0.733 kilonewton meter. So that would be 0.733 will be somewhere here because it's 1.33, 0.733. So now let me draw the bending moment diagram. That is your bending moment diagram. Okay. What is it telling you? That the maximum bending moment is at 1.468. Why are we calculating bending moment? In order to calculate bending stress, right? At each and every point on this domain, and then we would like to see what is the maximum bending stress. Correct? So let us look at it. So this is point B, C, A, E, and D. Good. So now let us calculate what will be the bending stress at B. Where will you have higher bending stress, at B or at C? It will be at B because the shaft diameter is the same at both B, point B and C, as we can see from here. And hence, the bending moment, the bending stress will be maximum at B because sigma B is equal to my by I. And y is the distance from the neutral axis to the outermost fiber. I is the moment of inertia. At both B and C, y and I are the same. And wherever you have maximum bending moment, that is where you are going to have maximum stress. Since B has higher bending moment, I am calculating stress at sigma B. That is equal to 1.468 times, what is y? Y is the distance from the neutral axis to the outermost fiber. Because it's a circular shaft, the shaft diameter is given as 48. So the distance will be half of that, that is 24. So that is 24 what? 24 mm. Please keep that in mind. So you have to work with consistent units, 24 mm. And here 1.468 MB is 1.468 kilonewtons. So I am writing it in newtons into 10 cube. So because 1.468 kilonewton meter, so that is Newton mm I will write. So that is 10 power 6 divided by I. I is pi d power 4 by 64. So pi d is 48 whole to the power 4 by 64 will come to the numerator. So all the units are now, this is Newton per mm square. Okay, because this I have converted it to Newton millimeter. This is millimeter. This is millimeter. So everything is in consistent units. So you have Newton per mm square. That is basically megapascals. And if you calculate that, that comes out to be 135 megapascals. That is your sigma B. Should we be happy with that, or because of the fact that there is stress concentration here, your actual bending stress, bending moment may be less, but because of the stress concentration, you may have a higher bending stress. So let us first calculate at sigma E, what is uncorrected bending stress will be me y by I, right? So that would be equal to me is 0.733 into 10 power 6 Newton mm. Y you should calculate with respect to the small diameter on the smaller side of E, that is 40 mm. So y will be 20. And pi d power 64, this 64 comes here, and pi into 40 power 4. So that comes out to be about 116.7 MPa, which is smaller than this value. So should we be happy? Not yet, right? We need to add the stress concentration factor. So the actual stress experienced by point E is actually the bending stress concentration factor. That is why we are given two, bending stress concentration factor and shear stress concentration factor. Now we are focusing on bending stress. Bending stress concentration factor times the nominal stress. This is basically the nominal stress. That will be what? 1.4 times 116.7. And that turns out to be 163.4 MPa. Now this is actually larger than this. So although the bending moment at E is smaller, because of the fact that there is a change in cross section, that point experiences higher stress, more stress than the point where the maximum bending moment is. This is a very important consideration that one needs to have while designing the component. So the maximum stress in the beam, the bending stress, maximum bending stress is 163.4 MPa. But mind you, this one is a rotating shaft. That means it is some sort of full, it is very similar to your fully reversed loading. That means what? Your sigma max is equal to 163.4 MPa and sigma min will be negative of 163.4 MPa. Okay? Which means your sigma mean is equal to 0 and stress amplitude, mean stress is 0, stress amplitude is 163.4 MPa. So much for bending stress. But will there be shear stress induced in the system? Yes, because the shaft is rotating, and there will be, because of the fact that there are shear forces acting on the beam, the shear stress tau max acting at point B will be 4 times shear force acting at B divided by 3 times area at the point B. This is what we call so VQ by IT, some formula that you would have learned in your strength of materials class. So this formula comes from there. So we are not deriving those formula here because they are something that you would have learned in the previous course. Okay, 4 VB by 3 AB. Okay, what is VB? VB is your shear force. So now we need to get the shear force diagram right. Okay, so let us get the shear force diagram right. And that is my A, RA, RB. This is 100, 200. Okay. So this is your, excuse me. So this is your E. 1 minute. Let me draw it to scale so that it is easy to. Okay. So let us say you're starting here, and 3 is 100. So this is your A, and that is your E, and another 3, that is your B. That is your D, right? So this is B. So from here to here, 200, and here to here, 200, and another 200. I am not drawing it. So, but let us assume this is B, but that is also 200. Okay. All right. So now you have at B and at C 8 and 6, and here you have RA, RB. We have already calculated RA and RB. So now if you would draw the shear force diagram at D, I am saying that it is 6.67, and then up to C it will be same, and at C I'm not drawing exactly below the C, but I hope you understand. And then this is 6.67 minus 6, so minus 0.67, it will come down to 0.67, and up to 8 it will be same, and then 8 minus 0.67 plus 8, that will be 7.73, and then up to here it is there. And so here you will have 7.73, and here you will have 6.67, and here you have 0.67, right? That's what you have. So at B, 4 times your VB is 7.33 kilonewtons. That means I have converted into newtons by multiplying with 10 cube by 3 into by 4. D is 48 square. That comes out to be 5.4 MPa. Similarly, tau max at E, what will be the tau max at E? So at E also shear force will be 7.33. All right. So 4 times VE divided by 3 times EAB, because at B and E the shear force will be the same. So that is 4 into 7.33 into 10 cube. But only thing that changes is the area of cross section, that is 40 square. So that makes it 7.8 MPa. So now this is the nominal stress. But what is the actual stress? Tau max at E is equal to KFS, the shear fatigue stress concentration factor in shear, times the nominal stress at E, that will be equal to 1.2 into 7.8. That will be 9.36 MPa. So now you have here, this is a rotating shaft again. Sorry, it is a rotating shaft, but with steady torque. If you see the question says that it has steady torque. That means what? The torque is not oscillating. It says steady torque if you read the question carefully. That means you have whatever tau that you are having is tau mean. The maximum tau mean is 9.36 MPa. And alternating component of shear stress is 0. That means you have a constant shear stress. Okay. So now let us write down what we have. You have a normal stress which has sigma mean is equal to 0 and sigma amplitude is equal to 163.4 MPa stress amplitude, and you have tau mean shear stress is 9.36 MPa. Our alternating stress due to shear component is 0, right? So now it is not a one-dimensional state of stress, it is a multi-axial state of stress. And hence what we need to do, we need to solve this problem as a multi-axial fatigue problem. So you need to calculate equivalent mean stress, that is equal to square root of sigma m square plus 3 tau m square. What is sigma m? That is 0 plus 3 times tau m square is 9.36 square. That is basically root 3 times 9.36. That comes out to be 16.212 MPa. And sigma, so equivalent alternating stress, that is equal to sigma a square plus 3 tau a square. Again, that is equal to sigma a square is 163.4 square plus 3 tau a is 0. Therefore, it becomes 163.4 MPa. Okay. Now, if you use Goodman criterion, according to Goodman, sigma m equivalent divided by SUT plus sigma a equivalent divided by SE is equal to 1 by factor of safety. So sigma m equivalent is basically 16 point. What was that? So now if you have to calculate your factor of safety will be equal to SE SUT divided by sigma ME times SE by plus sigma A times SUT. So what is SE? Endurance strength is 250 MPa and SUT ultimate tensile strength is given as 600 MPa divided by sigma M equivalent mean stress is 16.212 times endurance strength is 250 plus sigma A alternating stress is 163.4 times 600. That comes out to be 1.47. So the answer that is given in the exam is 1.5 approximately. Right? That is how you calculate the factor of safety for this problem. It is rather long, but it involves testing all the aspects that you have learned in doing the the solving a fatigue problem. Okay, all right. All right. So let me answer another question that was asked. I hope this question answer is clear. If it is clear about this question, please type in that you understood in the YouTube link. If you have any questions on this problem, please raise them now. Yes, that's a very good question, Mayank. The C factors will matter normally. So ideally what we should do in that case is we have not taken into account of the C factors because none of them were given to us in the problem. Normally, if you are doing a design problem in the class and when you are given all the design data handbooks, then you need to take into account of these C factors. But because of the fact that I have not provided you design data handbooks, normally what I would do is if you have to calculate the C factors, I will provide that value. If it is not provided, then assume it to be 1. Yeah, shear stress diagram. I will, Sardak, I am explaining you 1 minute. So, for those of you who are not familiar with drawing shear force and bending moment diagrams, that's how it is here. Okay. So you have this beam, okay, and it is subjected to 6. So 8 kilonewtons, 6 kilonewtons, and it is simply supported at point A, and this is point B, point C, and it is also simply supported at point D. Okay. So this is your, this I am calling it as reaction force at A and reaction force at D. Because of the fact that this beam is supported at these two supports, and the loads acting are here, there should be some reaction coming from the support. Okay. So then this 8 kilonewtons and 6 kilonewtons load has to be balanced by these two things. So I'm actually solving that problem for you. We know that you must have learned force equilibrium in your engineering mechanics course. So sigma F should be equal to 0. That is what we have learned. So that means RA, if I am taking upward force as positive, RA minus 8 kilonewtons at B minus 6 kilonewtons at C plus RD must be equal to 0. That implies RA plus RD must be equal to 40. Okay. And then sigma M must be equal to 0. That is another equilibrium. All the total moment should be equal to 0 at about any point. So I am taking it about a point A. I am taking moment about point A because that also should be equal to 0. That implies I am coming from this end, that is RD times. So we know the distances 0.2 meters, 0.2 meters and 0.2 meters. RD into 0.6 minus, I am taking sign convention into account, 6 into 0.4 minus 8 into 0.2 must be equal to 0. That will give me RD to be 4 by 0.6. That turns out to be 6.67. Okay, that's what we have actually shown there. Yeah. And similarly, then RA is equal to 14 minus 6.67, that is equal to 7.33. Yeah, I will do that bending moment diagram also. So now, in order to draw the shear force diagram, basically what does the shear force diagram tell us? What is the shear force experienced by the beam at each and every point? Okay. So now let us draw the shear force diagram. So for this, the sign convention is arbitrary, meaning you can actually choose upward force to be positive or downward force to be positive. It is up to you. But once you have chosen a sign convention, you need to stick to it. Okay, so let me draw the shear force diagram. So I am taking this baseline to be 0. Okay, that is my 0 line. And at RD, I calculated the shear force to be 6.67. My sign convention was what? Upward is positive. So both of them are positive. So I am saying this is 6.67. And then, even if you come here, there is no other shear force. If you are coming from D towards C, there is no other shear force in between, and hence, until a point right to C, very close to C, right to C, the only force that is experienced by the beam is, if you are looking from right side, it is only RD, and hence it remains constant up there, up till there. But at C, you have this downward 6 kilonewtons force. So at RC will be equal to RD minus 6, because RD is 6.67 minus 6, that is equal to 0.67. So let us say I am calling this is 0.67, meaning you have to normally draw to scale. Okay, this is my 0.67. Okay, so that is my point C. Now at point C, you have experienced effectively what shear stress? 0.67 kilonewtons shear stress. Now, if you move to the left, it will be exactly the same. Up to a little bit right to B, you will experience the same shear force because there is no shear force, any other force that is acting in between. So up to point B, it will be same. Okay, but at B, at RB is equal to 0.67 positive minus, because it's in the downward direction, minus 8. That becomes minus 7.33 kilonewtons. So because this is positive, I am going towards the negative direction, and minus 7.33, that will be little bit more than this height. That is my 7.33. And from here up to a very small, up to a very close to the right of point A, it will remain constant. But at A, it will be, sorry, it should be a horizontal line. And at C again, at A, it minus 7.3 plus this guy, this becomes balanced, right? So this is negative. That is how you will draw a shear force diagram. And then you have calculated the bending moment. Bending moment is what? Force times the displacement, the distance, momentum. So let us draw the bending moment diagram exactly on the same graph. Okay, this is my D, and that is my C, and that is my B, and that is my A. Because of the fact that it's free end, there is, so here you have a force acting at D. So the bending moment here will be 0 because there is no momentum. And here at C, we have calculated that bending moment at C will be RD times this distance. This distance is what? 0.2 meters. That is 6.67 into 0.2 that we have calculated it to be, I don't want to recalculate, so 1.334. So that is 1.334 at C. Okay. Then you might ask me 1.334. While drawing shear force diagram, I have drawn a horizontal line, but when I am drawing bending moment diagram, why am I connecting them like that? Why am I? The reason for that is, if you are calculating bending moment at this point, for instance, somewhere here, then the bending moment will be this times this distance, right? So basically the bending moment is changing from point D to point C linearly, and that is what is represented by this linear line. Okay. Similarly, you have to calculate bending moment at B. Bending moment at B will be this guy times the distance to that guy. What is that? 0.4. So RD, that is 6.67 into 0.4. And here there is another force. This guy is also going to cause bending moment at point B. So that is 6 into this guy, but it is in the opposite direction. So minus 6 into 0.2. So that turns out to be 1. What was the value that we have calculated? 1.468. That turns out to be 1.468 kilonewton meter. This is also 1.334 kilonewton meter. So that will be somewhere here. So this distance is 1.334 and that distance is 1.468. So this variation is linear from this point to that point. And now you know that bending moment at A is 0, because when you come from the left side, the bending moment at A should be 0. And hence you can, because there are no other forces between A and B, normally what you could do is, you could actually connect these two lines directly. That is what is your bending moment diagram. However, you can also calculate bending moment at A coming from RD. That is how we actually have calculated your reaction forces. That is 6.67 into 0.6 minus 6 into 0.4 minus 8 into 0.2. That turns out to be 0. And that's why you came here. This is how you calculate bending moment. And based on this bending moment value, we are actually calculating the stresses at each and every point. Okay. Is that clear? Okay. So then let me see what are the other questions. Okay. So there was a question in the live session, the Excel sheet that you have that has been shared with you about one of these things. So let me see those questions and then try to answer. Ah, so sir, please elaborate cyclic graphs in that you did in. What did I do? Please elaborate the cyclic graphs you did in multi-axial fatigue, and which is more conservative, Kf or Kt, and factors on which notch sensitivity depends. Okay, let me answer those questions by sharing the particular slides. Give me a minute. Uh, Ravi, I have some problem with my system. I need to, yeah, okay. I think I need to log off and log in again. Please give me a minute. Yeah, Ravi, I have a problem with my system. So I will log off and log in again. Please allow me. Okay. Ravi, can you hear me? Hello. Can you hear me? Yeah, yeah. So can I start now? Okay. Uh, I think my visibility is not a problem, right? I don't have to be visible, right? Or you want? Okay. Okay. All right. So the question. Yeah. So the question that I have here is the following. So let me answer that question. The question is, when okay, uh, so the question is, when we have the multi-axial loading, I think it was not clear uh, how this. We said one case is more complex than the other. So what we said there was is the following. So you have uh, a pressure vessel which is subjected to internal pressure. Then what you had was, you have sigma max and sigma min, and there was no tau. That means there was no shear stress. Okay. So you have sigma max and sigma min in two kinds of stresses. Basically, you have the hoop stress and longitudinal stress. So sigma 1 and sigma 2. That is, one is PR by T and another one is PR by 2T. So effectively, you will have some equivalent stress, but there is no shear stress. Right? However, when you have along with that, you have, let us say, steady torsion on this the pressure vessel. When you have steady torsion, you have sigma 1 varying like this, sigma 2 also varying like this, and you have a torsion, steady torque T, that is given by a tau given by TR by J. Then what we said was, your principal axis direction. So in this case, the principal axis, you will have some principal axis, you will have also some principal axis. The principal axis direction, that theta p, is calculated by 2 tau by sigma 1 minus sigma 2. So here also it is 2 tau by sigma 1 minus sigma 2. Here, since tau equal to 0, your principal axis direction is not changing. Here, however, the tau is non-zero, and hence the principal axis direction changes. So it is a multi-axial fatigue, but in addition to being multi-axial, the principal stress direction is also oscillating. So if you would plot theta p, it is not going to, in this case, theta p will be constant, but in this case, the theta p will be oscillating like this. So when the principal stress direction is also oscillating, then the way that you need to deal with your multi-axial fatigue is going to be a little bit more complex than what you would do when you don't have multi-axial fatigue. Okay, that was the question. So now let me go to the questions on phase diagrams one after the other, and then I will try to answer. Yeah, one question was, can you make arrangement of 2 to 3 numerical videos of previous weeks of 1 to 6 like it was done in week 7 and 8? So Sardak, I will try to do that. Sure. Okay, Anshuman, I will try to do some problems. Maybe in a week from now, we will try to, maybe we'll meet through Google Meet and then try to do that, not necessarily a YouTube live session. Okay. In variation of type 1 slide, Mayank, last example point states that there is no known example of maximum. So how in first point of this slide, it states that it is possible to have maximum as well. See, what Mayank was asking is the following. If you have type 1 alloy, normally this is our type 1 alloy. That's what isomorphous alloys. But then later we have said that you can also have something like this. This is with a minimum. And you can also have things like that. Right? This is with maximum.
And then we said that there is no known example of an alloy which shows maxima. Correct. Then his question is, why are you saying that it is possible? What it means is that thermodynamically it is possible, but we still don't know it. As of today, we don't have an example to actually show that there is no material system that we have observed to show this kind of a behavior. But it does not mean that that does not exist. It's only that we don't know. Thermodynamics, according to thermodynamics, it is possible that such a system exists, but it is simply that we are not able to, we have not been able to visualize it yet. So somebody in future might be able to visualize it and then may be able to give us that example. But thermodynamics does not forbid some system like that. So it is like the theoretically you actually show that it is possible, man, but experimentally it takes some time. See, for instance, as I mentioned in the class, in the discussion during dislocations, right? The dislocations were theorized to begin with. People actually theoretically have shown that for the finite strength of the material, there should be something called line defects, which probably are responsible for the reduced strength of the material than what you would expect, than what you would calculate theoretically, right? That we have discussed that. But later, only after some several years after the theoretical prediction has been made, people were able to see the dislocations experimentally. So it is not necessary that always experiments are done first and the theory comes later. It actually can be other way. For instance, you can actually talk about all of you probably heard of something called LHC experiment, Large Hadron Collider experiment. So that experiment actually proves the existence of Higgs boson. But Higgs boson was proposed to be existing. So the Higgs actually proposed that there is a particular particle called boson that should exist if you want to explain the physics of the problem, the Big Bang theory in principle. But later, it is only a theory until LHC experiment was conducted, and then people actually have seen that. Okay, so in that sense, you really don't have to have experiment coming first and theory later. It can be the other way around as well. It is good to remember certain things. For instance, copper nickel system is a good example for isomorphous system, and eutectic mixtures, eutectic alloys. You can iron carbon alloy system represents eutectic and eutectoid reactions, and you have actually seen other lead tin lead system showing eutectic reactions. It is good, but it is not essential. Okay. Yes, if a phase is brittle, what happens is your strength may increase, but the ductility will reduce. Right? That is what we mean by a brittle. Means it is hard to break, but if it is breaking, it breaks suddenly. That is what you mean by brittle material. So I understand, Subhankar, that normally we do this course after the strength of materials for the part on failure theories, because AICTE course suggests that failure theories be part of this program. So we assume that the strength of materials would have been done. But if you have not done the strength of materials, it actually is a full course that will be difficult for me to cover in 1 or 2 classes, but I can do the things like what I have done for the shear force and bending moment diagrams as I have done in today's class. And another question is, in type 2 alloy, in the graph done on hypoeutectic part, you told that the phase will be liquid plus A, which we know from tie line. But in liquid B is also present. So why B does not be in the part of diagram? So okay, let me draw type 2 alloys so that I know whether I made I have answered your question. Okay, so it should have been a straight line. So let us say this is my TA, and let me draw this in a different color, and let me say this is my TB, and we said and that is our TE, right? This is our TE. That is our type 2, where complete solubility in liquid state, no solubility in solid state whatsoever. Type 3 is partial solubility. We will discuss it later. So this is in liquid state, both A and B are completely soluble. So you have L. Okay, and this is A and that is B. Correct. So in this guy, to the left, in this is the two-phase region, you have liquid plus A, and you will have liquid plus B here. Why B here? Because if you draw a tie line, you are hitting this B line. So this liquid will have both A and B. But whatever solid that is formed, that will be only B. Here also, this liquid will have both A and B. But whatever A is solid A is formed, that will be only solid form, that is only purely solid A. Okay, that's what it means. So if you are cooling it down, so initially you will have liquid, and somewhere here if you see, you will have liquid and some A, and everything else is liquid. When I say liquid, this liquid is a liquid solution of A and B. Okay, that's how it is. I hope Sarthak, I have answered your question. If not, please let me know. Okay. So in type 2 alloy on liquidus, yeah, this is our liquidus, yes, line, it is written as pure A. Yeah. So when I say A, it is pure A. Why? Because in the solid state, A and B are not soluble. That means you cannot form a solid solution of A and B. So whatever solid that is coming out, it should be pure A, because when you are drawing the tie line, so this guy is hitting A and this is liquid. This liquid will still have both A and B. In liquid, you will have both A and B, but whatever solid that is forming before hitting the eutectic line, it will be only pure A. Yeah, this is liquid and liquid plus pure A. Okay. B does not come out as solid here because if you see in this region, so normally I would have drawn these phase diagrams from actually drawing free energy curves. So what happens is the free energy of A is lower than the free energy of B, solid A. So in this region, up to this temperature, up to this composition, the free energy of solid A is less than free energy of solid B. I have not told you those things because I have tried to explain these phase diagrams in not getting into too many details. So the key is the free energy. The free energy of solid A is less than free energy of solid B, and hence only solid A forms. However, after this composition, free energy of solid B is lower than the free energy of solid A, and hence only solid B forms. Did I answer that question? Oh, is my screen not shared? Shared, yeah. Okay. Yeah. Okay. All right. So the lever rule is pretty straightforward. Okay. I will explain the lever rule. So you have Okay, so this is my TA. I'm doing it TB. I'm doing it for type type 3 alloys. Okay. So that is point E. Okay. So now this is that. What is this type 3 alloy? This is complete solubility in liquid state and partial solubility in solid state. Since there is partial solubility, you will form a solid solution. So this is liquid, and let us call this as alpha, and this is called beta, and then this will be liquid plus alpha and liquid plus beta. Okay. So why do we need to use this Thailand concept is something that I would like to dwell upon a little bit. Okay, you have a liquid. It is a single phase region. So if you are having, so let us say I am talking about this particular composition, right? This is A and this is B, and this is pure A and pure B. And here I am talking about say 30% B. So if I am here, what is my liquid composition? Liquid composition is 30% B and 100% is liquid. Whatever is remaining, that is all is liquid. Good. Now, if you are coming up to here, fine. But now let us say you are in this region. Okay, you are in the two-phase region. Then what does it mean? You have some liquid and some alpha. So now the question is, your original liquid solution which you are cooling down has 30% B. But now the moment you come here, what is happening here? If you would look at the microstructure, this is all liquid. And let's come here. You have liquid plus some alpha. So I am drawing alpha with, this is my alpha, something like that. And remaining thing is liquid. The whatever is white is liquid. Okay. So this is my, I should have, that is my alpha. Okay. Now the question is, what will be the composition of this liquid? Will the composition of the remaining liquid, whatever it is here, is same as 30%? And what will be the composition of alpha? Okay. So then what you do is you draw a tie line. So let me draw it with a different color. And then this tie line, let us say this is A, this is point, let's say this is point O, and this is P, and this is Q. Okay. And now this tie line is hitting the liquidus at point Q. Wherever it is hitting the liquidus, and you draw a vertical line, and whatever may be the percentage, let us say this is 40%. That will be the composition of the remaining liquid in this region. Similarly, the tie line hit the solidus, this is solidus line here, and what is that is about 10%, let us say. That will be the composition of alpha. So at this position, the liquid composition is 40% B, alpha is 10% B. As you are coming down, the liquid is becoming richer and richer in B. That is what it means. Okay, there was no alpha, and now the alpha is forming. This is an alpha with 10% B. Now, what is the weight? So you have started with say 100 grams of your liquid solution. By the time you came here, you only have some liquid and remaining solid solution. So now the question is, what would be the weight of the liquid and what will be the weight of alpha? So the weight of the liquid, I have actually shown the derivation in the class. So the weight of the liquid would be PO divided by PQ. Weight fraction, in other words, weight fraction of the liquid will be PO times PO divided by PQ. So PO would be what? 20 divided by PQ is 30. That is 2/3. That is 0.667. That means 66.7% liquid will be there. And what will be the weight fraction of alpha? Alpha weight fraction will be QO, that is this part. This is a solid side, so you have to go to the other side, QO or OQ divided by PQ, that is 10 by 30, that is 33.33%. Sorry, 33.33% weight fraction of the liquid. So that means out of 100 grams, you will have 33.33 grams of alpha and 66.7 grams of liquid solution. Not liquid, but liquid solution. Alpha is also a solid solution. Yes. And then, okay, in type 3 alloy, the phase region below solidus line consists of alpha plus eutectic mixture or both alpha plus eutectic and beta plus eutectic. Okay. So good question. What you will have when you are coming, let us say you are cooling it down. By the time you reach here, just above this line, if you draw a tie line here, just imagine you are drawing a tie line, then the liquid composition is equal to eutectic composition. Let us say eutectic composition is 50% for the sake of argument. So the remaining liquid has got eutectic composition and the temperature is also eutectic. Whenever you have a liquid solution of certain composition, that is 50%, in this particular case, 50% B at TE, what will happen? An invariant reaction takes place. What is that invariant reaction? That is basically a eutectic reaction. All the liquid that is there will transform to two solids. What will be the two solids? The two solids will be alpha and beta, because here you have a solid solution. So two solids will be alpha plus beta. This is what we call eutectic mixture of alpha and beta. So by the time you are here, what actually you have is, if you would look at the microstructure, I will do a little bit better. If you look at the microstructure, you will have some alpha. Let us say all that is alpha and remaining is liquid. And then by the time you cross this guy, what happens? The remaining liquid, alpha cannot be transformed again because it's already transformed. Whatever is the remaining liquid, that remaining liquid will have no option but to go through this reaction. So you will have eutectic mixture of alpha and beta. This hatched region is actually, this is alpha, and whatever is to give you a better idea, let us say that is beta. The black lines are alpha, red lines are beta. Let us assume like that. So what you will have is, at the bottom below the solidus line, you will have primary alpha, that is pro-eutectic alpha, and eutectic mixture of alpha and beta. Okay, that is what you will have. But if the same thing, if you do here, if this composition is cooled down, what you will have is pro-eutectic beta and eutectic mixture of alpha and beta. So you, in this region, you will have some eutectic mixture of alpha and beta, but alpha and beta can actually appear in different fashions depending upon what composition you are looking at. If you are looking at this composition, you will not have any pro-eutectic composition because all that is liquid is transforming to alpha plus beta. So you will only have eutectic mixture of alpha and beta. Okay. Yes, Subhankar, very good question. Most of the binary phase diagrams, the curves are mostly between temperature versus composition. Can it be between other two variables like pressure versus composition and temperature versus pressure? I think this is an assignment question, a tutorial question. So I would like you guys to think about it. And I will answer this question in the next class. Otherwise, I would be answering this for your tutorial. So please think about it. If we heat an unsaturated sugar solution and then keep that solution in refrigerator, then shall the solution become saturated or still remains unsaturated? Okay, so you have an unsaturated liquid solution, right? But you are actually cooling it down. So that means you have, let me think about it carefully. You have an unsaturated sugar syrup, and then you heat it, you have cooled it down. So imagine this way. What might happen is that because you are freezing it, so that means you are actually bringing it to solid state. In the solid state, you have some finite solubility of sugar in water. So some of the sugar might actually precipitate out. So let me give you an example. Many of you would have seen bundi laddu made, right? When you see bundi laddu freshly made, you don't see sugar crystals, the white sugar crystals coming out, right? But over time, that white sugar crystals comes out, and you can see actually a sugar dust on the surface of the bundi laddu. Why is that? Because this additional sugar is not able to stay in the solution state, because in the solid state there is finite solubility, and hence it is coming out as uh, a sugar as it is. But if there is finite solubility, if the solubility is not undersaturated, it is if it is oversaturated, then it will come out. But if it is undersaturated, there is no reason why it should come out. Okay. Yes, I have drawn the tensile strength variation in terms of, so you have seen that copper nickel system in the isomorphous alloys. I have drawn, let us say this is composition. So this is copper and nickel. Let us say copper has some tensile strength, nickel has some tensile strength. I've shown that you will have a peak, right? So even when you come from nickel side, you will have increase in tensile strength, but after that it reduces. Again in copper side, you will have an increase in tensile strength, and then it reduces, right? Why does that happen? Because this strength has to do, there are different kinds of strengthening mechanisms that we have studied in our mechanical properties of materials, or in the case when we have discussed dislocations and so on. The reason for that is that there is something called solid solution strengthening. That means now when you have nickel as an impurity in copper, that basically solid solution is by nothing but you have pure copper. To that pure copper, you are adding impurities of nickel, right? So now what happens is this impurity, nickel impurity, will act like a barrier for dislocation motion, and that is the reason why you will see an increase in tensile strength. Similarly, if you take pure nickel has some tensile strength, but if you are adding copper, so if you on this side you have if you take this solid solution is rich in nickel and poor in copper. That means here the solute is copper, solvent is nickel. If you come here, the solute is nickel and solvent is copper. So now in the nickel matrix, copper atoms act as barriers to dislocation motion, and hence you will increase the strength of the material. Okay. And there was another question: how does what are the parameters on which the notch sensitivity depends? Notch sensitivity depends on the geometry and the mechanical property of the ultimate tensile strength of the material. So that is why if you would see the plot, you have geometry as well as ultimate tensile strength coming in, and that is what is going to decide your north sensitivity. Okay. What do you mean by pro-eutectic? Pro-eutectic means the alpha solid solution that is formed before the eutectic reaction takes place. See, up to here, you have, say, when you are cooling it down, up to here, your sum of your liquid is transforming to alpha solid solution. But the moment you are below this, the remaining liquid is transforming to eutectic mixture of alpha and beta. So, pro-eutectic means, pro means before. So, it is formed before the eutectic reaction took place. That is what is the meaning of pro-eutectic. I mean, notch sensitivity factor Q depends on geometry and ultimate strength of the material, notch sensitivity factor. Okay. Any other questions? Did I miss any of the questions? Liver rule I have explained. Mayank Mishra. Okay. See, solid solution itself is a so solid solution is nothing but you are actually adding impurities to a pure metal, right? And as I have explained the strengthening mechanism here, that is mainly because you are adding impurities to your parent phase. Okay. So if notch sensitivity depends on geometry and yield strength, how does it increase in torsion than axial loading? So I am not sure if I understood your question clearly, Mayank. Can you please send me an email and then try to explain, and then I will try to answer that through email or in the next live session. Okay. All right. If there are no further questions, we will stop here, and then I will send you about meeting link again for live interaction. As you requested, maybe we will try through Google Meet, where you can ask questions by unmuting yourself. That is, I will explore that that option in the next meet. Yeah. Any other questions? Did I miss anyone? Yeah, I will, Subhankar, I said I will give you some practice questions. I am working on it. I will provide you guys with some practice questions. Okay. Thank you. Bye. Ravi, I think I am done.